All right, so any questions before we get going? What were we doing? We were talking about graphs. Yes?
On a directed graph, if you have an edge that goes both ways, do you put 2 arrows or just no arrows?
It's kind of, either one's probably fine. I don't know if there's a formal answer to that, like you must do this or that, but for yeah, for our sake, I'd be fine with an arrow going both ways. The only warning is when you're doing things like counting degrees, right? Sometimes it's going to be less ambiguous if you have 2 arrows drawn, 2 paths with different directions. So that might be the preferred way. So let's talk about isomorphisms of graphs, right? We had this notion that it's really bright in here. We had this notion that here's a graph, right? And this is A, B, C, D. And here's another graph. And at first glance, they kind of look different from each other, right? But in fact, they're exactly the same graph. If you look at each graph, it has 4 vertices, 4 edges. We have an edge connecting A and B, an edge connecting B and C. I lied. There we go. An edge connecting B and C, one between C and D, and one between A and D. So now these are exactly the same graph. And if you could lift this off the page, right, you could just move these 2 vertices in each other's place and put it back down on paper and you get this thing, right? So looking at it, it's potentially deceptive. It's not clear that this is the same thing. But we'd like a way to be able to say that, yes, these are the same or they're different. My screen's being a little weird. It's magic. Damn. Okay. That's annoying. Yeah, it's a glitch. So we can talk about graph invariance. So we can use the term isomorphism. And isomorphisms are sometimes drawn with an equal sign with a little tilde on top. Isomorphic, same shape, basically. So a graph invariant is something about a graph that does not change among isomorphic graphs. Okay, for example, this graph on the left has 4 vertices. No matter how we change the shape, no matter how we stretch it or move things around, it's always going to have 4 vertices. Okay, so one graph invariant is the total number of vertices in the graph. Similarly, another invariant is the total number of edges. But the size of the graph is definitely not an invariant because this is isomorphic as well. Right? It takes a lot less space on the page. And similarly, the shape is definitely not an invariant. But the number of edges and the number of vertices are invariants. And if those are invariants, remember if we add up the degrees of each edge, we should get twice the number of edges, right? So the sum of these degrees should also be an invariant. But more than that, the set of degrees across all the vertices should also be invariant. For example, I have 4 vertices and they each have degree 2. So in an isomorphic graph, I should have 4 vertices and they should each have degree 2 as well. So if I have a graph like this, I know right away this is not isomorphic. Because I have two vertices of degree 3 over here, and I don't have two vertices of degree 3 in this original. So the set of all degrees, we call it the collection of all degrees, that's also an invariant. It's not a set because we might have the same number more than once. But if we take the collection of all of the degree of each vertex, right, that's going to be an invariant. So looking at graph invariants, we can immediately tell sometimes if two things are not isomorphic. Right, if they have different numbers of vertices, different sets of degrees, and so on, we can say they're not isomorphic. But if these invariants match up, we still can't say that they're isomorphic. Okay, they may or may not be. So let me see if I can do a quick example. So 4 vertices, 5 edges, and the degrees of the vertices over here are 2, 2, 3, and 3. The degrees of the vertices over here are 2, 2, 3, and 3. Those invariants match up, but these are not isomorphic graphs. And we can sort of convince ourselves of that because there's a pair of vertices with 2 edges connecting them over here, and we don't have that situation over here. There's only a single edge between any 2 vertices, so those are not isomorphic. So telling when 2 graphs are isomorphic is a hard thing. I think it's one of those NP problems, right? Computationally complex. But here's what we can do. If we can find a way to map vertices from one graph to another that preserves the adjacency of edges, then we can say the graphs are isomorphic. In other words, if we can rename the edges, the vertices, in a way that preserves what's adjacent to what, then we can establish an isomorphism. So here's A, B, C, D, and here's W, X, W, X, Y, and Z. And so can we find a mapping, injective and surjective, between these vertices and these vertices, such that we preserve adjacency? So for example, if we take A and map it to W, take B and map it to X, take C and map it to Z, and take D and map it to Y, then our adjacency is preserved. We have an edge connecting A and B. We have an edge connecting W and X. BC corresponds to XZ, that's that edge. CD corresponds to ZY, that's this edge. And DA corresponds to YW, that's this diagonal edge. So that's the way to tell that 2 graphs are isomorphic, is to find a mapping between the vertices of one graph and the vertices of another. If there's a bijective mapping between those that preserves adjacency, then the graphs are isomorphic. And if there's no such mapping, then they're not isomorphic. But finding that mapping is a hard thing. Because if you have n vertices, and you're trying to map into another set of n vertices, how many possible maps can we establish? How many ways can we map n things to n things?
N squared. Was it? No, It's like n should.
Yeah, it's n factorial, right? So use a product rule to establish a mapping. We have a set of tasks. First we have to map vertex 1, then map vertex 2, vertex 3, vertex 4, and so on. So the first vertex we can map to any of the n vertices in the second graph. The second vertex we can map to any of the unmapped n-1 vertices. The third vertex we can map to any of the remaining n-2 vertices, and so on. And so there's a total of n factorial bijective maps from the vertices of this graph to the vertices of this graph.
Can you have a connection to yourself?
Sure.
Okay.
Yeah, that's still valid if it goes to itself. Well, these are mappings from one vertex to another.
Well, it's just like,
But
oh,
yeah,
you would
as-
you just say n-1 factorial, because the first one wouldn't have n options, it would have everything but itself. If you didn't.
Well, no. So we're mapping from this set of vertices to this set of vertices, right? So we're trying to find a function which goes from this set to this set. So there is no a over here,
Okay.
right? We're trying to make a function so that f of a
I see.
equals something, f of b equals something. And we did this when we did counting, right? We looked at how many bijective functions there were from one set to another. And it turned out to be horrible. Right? So if you wanted to exhaustively tell whether or not there's an isomorphism, you could take all of these n factorial possible maps and see if any of them preserve adjacency. And if they do, you're isomorphic. If not, you're not. But for a graph with 100 vertices, that's a huge amount of work. 100 factorial, big. All right, so let's talk about paths. And we're leading up to talking about shortest paths and something called Dijkstra's algorithm. But there's some things we can talk about with paths themselves. So, definition, a graph is called connected if any two vertices are connected by a path. All right, well, what's a path? Let me just give you a picture of it. So A, B, C, D, E, F. So a path from A to E would be to travel from A along this edge to C, and then travel along this edge to D, and then travel along this edge to E. That's a path from A to E. So it's a series of edges starting at our starting point, ending at our ending point, and with the property that the end of each edge is the beginning of another edge in our set. And we can make that really long and wordy. But that's the basic idea. It's a bunch of edges that are connected end to end that take us from one point to another. Another path from A to E would be to go along here to C, and then go along here to D, and then go to E, and then go to F, and then come back to E. Technically, that's still a path. It starts at A and it ends at E. And in fact, once we get to E, we could go back to F again, and we could come back around to E, and we could go back to F, and we could come back around to E, and that's still a path. But it's a more complex path. And it's in some sense needlessly complex because we already reached E when we left D, but then we just did a few loops over here. But it's still a collection of edges starting at A, ending at E. So this is sometimes called a simple path, A, C, D, E. And this would not be a simple path because it's revisiting things that it's already visited. All right, so a graph is connected if between any two vertices you can get from one to the other along a path, which means if we throw in an extra vertex over here, this is no longer a connected graph. This is a connected graph, this is a connected graph, but the whole thing, right? We have no path from G to D, for example. All right, a special type of path is called a circuit. So a circuit is a path that begins and ends at the same vertex.
So can you have a circuit as part of a bigger graph? Is that like some kind of subgraph?
So here's a circuit, for example, this loop from E to F and back to E. And that could be a part of this complex path, A, C, D, E, F, E. All right, so paths just go from one vertex to another. Circuits go from a vertex back to itself. And when we're talking about circuits, if we allow anything, right, there's always a circuit from any vertex back to itself. For example, we go from A over to B and then back to A. But we're not really interested in that. That's kind of cheating. Okay, so we're mostly going to look at paths where we don't travel along an edge more than once. Okay, so that's going to be this idea of a simple path. All right, so an Euler path. Is a simple path that contains each edge exactly once. I'm not going to use the word simple. There's different interpretations of that term, so I'll just avoid it. So an Euler path is a path that contains each edge in a graph exactly once. So here's the classic example. So can we find a path through this graph that contains each edge exactly once?
Yes.
How do we do it? Where do we start?
So bottom left,
Okay,
go up.
up straight.
Yeah.
All right,
And to the top.
go up to the top. And I'm drawing arrows here, not because it's a directed graph, just to help us see where we're going. So we're going to come back down.
Down to the bottom right.
All right,
Then up the diagonal.
up the diagonal,
And across.
cross.
Why do you do that way?
Back And did we cover each edge? And did we do any edges more than once? Okay, so that's a valid Euler path. Good. Now we hit some vertices more than once. That's okay. You're allowed to do that. For an Euler path, the goal is to travel each edge once and only once.
Is there an Euler circuit where it has to?
That's a good question. An Euler circuit is an Euler path that's also a circuit. Is there an Euler circuit for this graph?
Yeah, there's one.
All right.
Keep everything and just at the corner of the block.
Yeah, I see one.
No,
You see one?
no, just down
Here. Come on up. I'll make you a new graph. All right. That's okay.
there.
Use a different color if you want. Different green. So you're discovering a key fact here, though. So did you have an idea?
There was wrong.
Okay. So I saw you struggling around here, right? This is the key to understanding Euler paths and Euler circuits. The problem with this graph is there's an odd degree right here, and there's an odd degree right here. Okay, what does it mean when you have an odd degree, an odd number of edges going into that vertex? It means that as we're drawing a path, anytime we come into this vertex, if we leave, we're going to consume 2 edges. And if we come in again and we leave, we're going to consume another 2 edges. Ultimately, we have to consume an odd number of edges. And the only way we can do that is by either starting at this vertex and drawing an edge away, or by coming into this vertex and then not drawing anything else. So we can begin or end at these vertices with an odd degree, but we can't begin or end anywhere else, right? If we began here, this would end up having an odd degree. Same here, and these have even degree, right? 2, 4, and 4. These have odd degree, 3 and 3. So by struggling and trying to find an Euler circuit, what we're faced with is this idea that if we were to begin and end at the same vertex, that vertex would have to have an even degree, because we'll use an edge to leave in the beginning, that's 1. And then we may enter and leave multiple times, but it's still going to be an odd number of edges we've traveled on. And then if we're going to finish at that vertex, that's going to be 1 more edge. That's going to be a total of an even number of edges. It'll have an even degree. And so, since every other vertex that we don't begin or end at has an even degree because we enter and we leave, the only way we can have an Euler circuit is if every vertex has an even degree. And that's a theorem. That's one of Euler's contributions to this. So this graph right, this does have an Euler circuit. In fact, I just used one to draw this. And that works because every vertex has an even degree.
So the classic 5-point star is an Euler circuit, like when you draw.
Like that?
Yeah.
Yeah. And in fact, if we wanted to connect the edges, that's still an Euler circuit, and if you look at the degree, everything should have an even number. It looks like 4 for each vertex. So there's a theorem here. So if we have a graph G with vertices and edges, so it has an Euler path. If and only if every vertex has even degree, or exactly 2 have odd degree. And if every vertex has an even degree, then G has an Euler circuit. So there was a famous puzzle in, I don't remember where it was, but it's where Euler was. There was a area of town where there were, I think, 7 bridges, and there were some islands, and you could travel across these little walking bridges to get to an island. And the question was, could you start at one point and walk across the bridges and visit every island without ever crossing a bridge more than once? And it's basically a question, is there an Euler path or an Euler circuit through the graph corresponding to that little section of town? And he was able to answer that and say, no, you could not do that, and was able to explain why. All right, so that has an Euler path and it has an Euler circuit. All right, we can come over here, come down, across, come over and up. So that has a path and a circuit.
You can have an Euler path with 1 odd degree, can't you? Or with, I'm sorry, with 1 vector having an odd degree. So you just start there, right? And then you can just go wherever.
You start there, but where are you going to end? Right, so wherever you end, every vertex that you visit on your path, you're going to have 2 edges, one that you use to arrive and one that you use to leave. So if you don't end at one of those, then you have to end where you started, and that's going to make that an even degree. So I think it has to be exactly 2 or 0.
I don't think you can have an odd number of vertices of odd degree.
That's a good question too.
Oh, that's, yeah, but not.
No, you can't. We proved that yesterday. Right? The number of vertices of odd degree must be even, because the sum of those degrees has to be even. So if you had all even degrees except for 1, the sum of the degrees would be odd, and it can't be twice the number of edges. All right, so this graph down here, we've got 1, 2, 3, 4 edges with odd degree, 4 vertices with odd degree, so this has no Euler path and it has no Euler circuit. And our house drawing has a path, but no circuit. All right, so Euler paths talk about visiting edges, right? You want to visit each edge exactly once. There's a dual concept, which is called a Hamilton circuit or a Hamilton path. So a Hamilton circuit or path is a circuit or path that, what's the dual is going to be? Instead of visiting edges once. Vertices. What if we wanted something that visits each edge exactly twice? Would that be a thing?
Just be doing Euler path twice.
Yeah, if it's a circuit, we can just do the circuit twice. And if it's a path, if it's undirected, we could go from A to B, and then we could go back from B to A, and that would visit every edge exactly twice. So I think we get those for free. But visiting each vertex exactly once is a very different kind of thing. So is there a Hamilton circuit in this graph? Yes. So we can start here, come up, go across, come over, come down. And in fact, there's a Hamilton circuit if we go back to the beginning.
Wouldn't that touch the first vertex twice?
Yeah, I'm not sure how to define a Hamilton circuit. Visits each vertex exactly once except the starting and ending vertex. I don't even know if it's a thing.
Is there actually a circuit for Hamilton?
Yeah.
Well, because if you end where you started, that means you visited the vertex twice.
Yeah, so that one you're going to have to be allowed to visit twice.
Yeah.
So let's find something without a Hamilton. So that one I'm pretty sure there's no Hamilton path for.
Wait, so you can like skip edges, right?
You have to travel along an edge. You're not required to touch every edge though.
Yeah.
But you have to, it has to be a path.
And it just has to touch every vertex?
Oh yeah, okay, so that's good. That does work.
What the works the path and not circuit?
Yeah, so we can do that. I want a graph that doesn't have a Hamilton. $50 for the first one, no.
What if you got rid of that starting point and then you just had that second one go,
This?
like the top left one,
Mm-hmm.
and then the one below it went directly to the next one on the bottom?
Hmm.
Oh,
Wait. Could you just go there?
It's usually really hard to find a Hamilton path, so.
so I go with one. That was
Okay, that one should do it.
decent. Yeah.
We don't even need all of this stuff over here. But the problem here is if we start with this vertex, we can get to exactly one of these, but we can never come back, right? And if we start with, say, this vertex, we've got no choice but to come here. And then we can either visit this and be done, or visit this and be done. And we can never get to all three of those. So that's a simple example of a graph with no Hamilton path. And there's no nice criteria for Hamilton paths like there is for Euler paths. Euler paths, we have this nice rule we can use, just find the number of vertices of odd degree. If it's 2, start at one of them, end at the other, and it usually just draws itself. But for Hamilton paths, there's no simple criteria. It's generally a really hard question. Up there with, like, the NP stuff. Which is a little weird because it's really just kind of a dual to what we're doing with edges. So let me show you one application of Hamilton paths. Alright, so here's our nice cube made of toothpicks. And I'm going to label these coordinates. So I'm just labeling these with spatial coordinates. So each vertex should have a unique label. 0, 1, good. Okay. And it's a graph. It looks three-dimensional, but it's still just a graph, right? It's vertices and edges. And the question is, can we find a Hamilton path through this graph? And I want to start right here, for example. And so, yeah, we can come up here and we can come across and come down. And I can't go over, so I'm going to go back at this point. And come over like this, and come up, and come over. And that should hit all my vertices exactly once. That's not what I wanted. Well, that's okay. All right, so what's interesting about this graph? Since these vertices also correspond to spatial coordinates, if we were to think of this as a three-dimensional cube, and the edges of this cube are parallel to our axes, what happens to the coordinates when we move from one vertex to a vertex connected to it? we're traveling parallel to an axis. And at most, one of our coordinates is going to change. When we move from this point to that point, our z coordinate changes from 0 to 1. When we move from this point up to this point, our y coordinate changes from 0 to 1. When you move parallel to an axis, two of your coordinates will stay the same, and the axis you're traveling along will change. So, along each of these edges that we visited in our path, exactly one coordinate changed. So it's like a state machine. It's a little better. If we write out these coordinates in order, what this means is that from one number to the next, only a single bit is changing. Right? This is like a gray code, which we talked about when we studied state machines in 250. Gray codes are nice because you can avoid certain race conditions. When you move from one value to the next, say from here to here, the only thing that's changing is this one bit. It might change quickly, it might change slowly, but it's going to change as a number from this value to this value. As opposed to our regular way of counting, where when we change from 3 to 4, we could find intermediate states where, for example, this bit might change first, and then maybe that least significant bit changes, and then maybe that middle bit changes. And so we go from 3 to 4, but we also pass through these intermediate states, right? That's the source of glitches in a state machine. Because this might be the state that says emergency shutdown. And even though you're only briefly in that state, your whole system changes because of it. Now this was a bad gray code because when we go from here, we didn't make a circuit. But if we had done a Hamilton circuit, that would let us come back to 0, 0. Then we'd have a nice gray code. So what would that look like? Start from 0. Let's go up and over and down. Sorry, let's go up and over and back and across and down and out here and back and then back like this. And so if we do that, our coding is 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 0, 0, and then back to 0, 0, 0. And that's your classic reflective gray code. So we can keep counting 0 to 8, 0 to 7, and preserve this single bit changing property. All right, so that's just a 250 tie-in. So I mentioned the other day that edges can have weights associated with them. So suppose we have a weighted graph like this, and we want to travel from some vertex A to another vertex B. And we want to find the shortest path from A to B, where shortest means in terms of adding up the weights or the lengths of these edges. And there's multiple ways to get from A to B. We could go from A to this vertex to B. We could go from A to this vertex to B. And in this case, going from A to here, let me call these something else. Let me call this C, D, and E. Going from A to C to B is going to have a total length of 10. Going from A to E to D to B is going to have a total length of 11. But if this had a edge of length 2, right, A, E, D, B, has a total length of 9, whereas ACB has a length of 10. And this is what makes shortest path problems tricky, is that this path has more edges, but it has the shortest total length. This path is much more direct in some way, but it's longer. And when we ask for a shortest path, we're not worried about how many edges we have to travel. We're worried about what's the smallest sum of the weights of those edges. And so what I want to look at tomorrow is this problem in some detail of finding shortest paths. And we'll look at an algorithm called Dijkstra's algorithm. And that's your last homework problem, I think, for Thursday is using Dijkstra's algorithm. So we'll work through that in detail tomorrow. We'll go through some examples. I might have you go off onto the board and work in groups and apply this. And that's a good stopping point for graph theory then. All right, so I will see you tomorrow. Yeah.
So for a path, as long as it's just a path through points, it doesn't have to be a vertex, and use edges.
A path is just going from one vertex to another, to another, to another. You can visit vertices multiple times, you can visit edges multiple times. But visiting edges multiple times makes it non-simple. And we usually talk about simple paths.